At 2:47 a.m., a Fortune 500 company's automated procurement pipeline went completely dark. Not because the LM failed. Not because the API was down. A single subagent, responsible for validating their contracts, hit a 30-second timeout waiting for an external compliance tool. That one stall was enough. The orchestrator, receiving no response, held its execution thread open. Downstream agents queued up, waiting for a signal that never came. Within 4 minutes, the entire pipeline was deadlocked. 47 concurrent workflows, frozen. This is a cascade failure, and it is the single most underreported failure mode in production multi-agent systems today. Engineers celebrate when their agents talk to each other. Nobody talks about what happens when one of them stops talking. The question you need to ask is not, can my agents communicate? It is, what happens to every other agent when one goes silent? By the end of this lecture, you will have the architectural vocabulary and the design patterns to answer that question definitively. This failure did not happen because the engineers were incompetent. It happened because they treated their multi-agent system as a workflow tool, not as a distributed system. When you wire agents together, one calling another, results flowing downstream, you have created a dependency graph, and every dependency graph carries what I call distributed systems debt. The accumulated risk of unhandled partial failures, missing circuit breakers, and absent idempotency guarantees. We solved these exact problems in microservices architecture between 2010 and 2018. Netflix built Hystrix for circuit breaking. AWS designed bulkhead patterns for fault isolation. The CAP theorem forced us to reason about consistency under partition. But today, teams building multi-agent AI pipelines are repeating every single one of those mistakes. Because the tooling looks different, the vocabulary is different, and the lessons were never carried over. Here is the critical insight. An agent dependency graph is topologically identical to a microservice call graph. The failure modes are the same, the solutions are the same. Only the implementation layer has changed, and that realization is the foundation of everything we will build in this lecture. Let me be precise about what this lecture delivers, because vague promises waste your time. By the end of 6 chapters, you will have 3 concrete design capabilities. First, you will be able to classify any multi-agent topology, whether it is orchestrator-driven, choreography-based, or hybrid, and articulate the exact failure mode profile of each. This is the kind of architectural reasoning that separates a senior architect from someone who just connects API calls. Second, you will be able to map every major failure mode, timeout, partial failure, state inconsistency, context overflow, to its corresponding engagement pattern, drawn directly from distributed systems engineering. Not vague advice. Specific, implementable design decisions. Third, you will understand where the Model Context Protocol, MCP, sits within this architecture, why it matters for tool call standardization, how to evaluate whether your system actually needs it. These are not academic outcomes. These are the decisions you will face in your next production architecture review. And the gap between knowing these patterns and not knowing them is between a system that scales and one that collapses at 2:47 a.m. Here is the map of the journey we are about to take, and why the sequence is deliberate. Open here in Chapter 1 by establishing the failure reality. Multi-agent systems collapse in predictable ways, and those ways have names. Chapter 2 reveals why single agents hit a scalability ceiling. Context windows, latency and complexity, task complexity create a hard boundary that forces you toward multi-agent design, whether you want to go there or not. Chapter 3 is the analytical core. We classify every major agent topology using a framework borrowed directly from distributed systems theory, and we map each topology to its failure mode profile. Chapter 4 applies 25 years of distributed engineering principles, specifically the 8 fallacies of distributed computing, directly onto agent architecture decisions. This is where experience becomes leverage. Chapter 5 builds a real reference architecture from the ground up, orchestrator scope definition, subagent contract design, and fault isolation boundaries. And Chapter 6 integrates MCP, the Model Context Protocol, showing exactly where it fits and where it does not. Each chapter is a layer. Skip one, and the next one loses its foundation. Now, before we go further, let me show you why even the best designed single agent will eventually force your hand toward multi-agent architecture. That ceiling is closer than most teams realize. Let's start with a deceptively simple question. What exactly is a single agent doing when it runs? The execution model is a tight loop. Perception, reasoning, action, observation, repeated until a terminal condition is met. The agent receives input, builds a reasoning trace inside the LLM, emits a tool call or final answer, then absorbs the tool's output back into the same context window. Every single iteration appends tokens. The context window is not a queue, it is a finite register. Once saturated, you do not get slower performance, you get hard failure. The model either truncates its own memory or the API throws a limit error. This is the first architectural ceiling, not a warning, a wall. And here is what makes this dangerous in production. Most developers only discover this wall when a real workload hits it. But there is something even more subtle lurking inside this loop that we need to expose in the next scene. Now let's visualize what actually happens when you assign a complex, multi-step task to a single agent. Imagine a financial audit task: retrieve data from 5 sources, reconcile discrepancies, generate a compliance report, and draft an executive summary. A single agent must call these tools one after another. Sequentially, it cannot parallelize. While tool number 3 is running, the agent sits idle, and its growing context is holding every prior result from calls 1 and 2. By the time you reach call 5, the context window is so loaded with intermediate results that the reasoning quality begins to degrade before you even hit the hard token limit. This is a dual failure. Latency explodes because sequential tool calls chain their wait times, and accuracy collapses because attention across a bloated context becomes diluted. In distributed systems, we solved this exact problem 40 years ago with horizontal partitioning. The pattern is identical, but most AI architects are rebuilding the same mistake from scratch. Let's now ask whether the new generation of massive context models changes this equation. And the answer will probably surprise you. Here is a claim you will hear frequently. We do not need multi-agent design anymore. Qwen 3 and similar models support 1 million token context windows. Let's stress test this claim with data. First, empirical research on long context transformers, including studies by MIT and Google DeepMind, consistently demonstrates what is called lost in the middle degradation. Retrieval accuracy for information positioned in the center of a long context drops significantly compared to content at the edges. This is a attention illusion at scale. Second, the cost curve is brutal. Processing 1 million tokens in a single call costs orders of magnitude more than decomposing the same workload across specialized subagents operating on focused, small contexts. Third, and most importantly, throwing more context at a problem does not grant parallelism. A 1 million token single agent it still fails atomically. It still has no fault isolation. The 1 million context window is a useful tool, but it is not an architectural substitute for decomposition. The architects who understand this distinction are the ones building systems that actually survive production. Next, we are going to see where this pattern was solved before, in a field that has nothing to do with AI. If you have spent time in enterprise software architecture, this problem will feel deeply familiar because we have been here before. In the 1980s, enterprise applications were monoliths. A single codebase, a single database, a single deployment unit. As workloads scaled, these monoliths hit their own walls: deployment risk, scaling limits, team coordination failures. The industry responded with service-oriented architecture in the late 1990s, decomposed the monolith into coarse-grained services with defined interfaces. Then came microservices in the 2010s, finer decomposition, independent scaling, fault isolation at the service boundary. The pattern is always the same. When a single unit can no longer scale vertically, you decompose horizontally and introduce coordination mechanisms. Multi-agent AI is not a novel invention. It is the software industry running the same playbook for the third time in a new domain. The architects who built Netflix's microservices transition or Amazon's service decomposition were solving the same core problem we are solving now: LLM agents. But decomposition always introduces a new challenge, and that challenge has a name we borrowed directly from distributed systems theory. Now I want to make this mapping explicit, because as this is the intellectual core of this entire lecture series. Every principle from distributed systems theory is a direct analog in multi-agent AI design. Consider the CAP theorem. In a distributed system, you can guarantee at most 2 of 3: consistency, availability, and partition tolerance. In a multi-agent system, the equivalent trade-off is between result consistency across agents, system availability when subagents fail, and partition tolerance when interagent communication breaks down. Consider eventual consistency. Distributed databases like Cassandra accept temporary divergence in exchange for availability. Multi-agent systems exhibit the same behavior when subagents asynchronously and reconcile results later. Consider circuit breakers from Netflix's Hystrix. In multi-agent terms, an orchestrator that stops delegating to a repeatedly failing subagent is implementing a circuit breaker pattern. These are not analogies for illustration, they are the same design patterns, applied to a new substrate. The engineers who internalize this mapping will design agents. The Lamport and Brewer designed distributed systems with formal rigor, not intuition. Let's close this chapter with a signal from the market that confirms exactly what we have been building toward. Google's internal agent bake-off, a competitive evaluation of AI system architectures across enterprise workloads, reached a conclusion that should be required reading for every AI architect. Multi-agent systems combined with multimodal reasoning are the emerging production-grade standard, not single agents with larger context windows, not prompt engineering tricks. Structured multi-agent orchestration with domain-specialized subagents, multimodal perception, and fault-tolerant coordination. This is not a research paper claim. This is a production benchmark finding from one of the largest AI deployments on the planet. The urgency for architects is this. The teams that learn to design these systems now will define the enterprise AI infrastructure of the next decade. The teams that do not will be integrating someone else's architecture. We have established why single agents fail and why multi-agent design is the inevitable architectural response. Now comes the question every architect must answer. What topology do you choose? In the next chapter, we will dissect the three fundamental orchestration topologies, centralized, peer-to-peer, and hierarchical, and show you exactly when each one will save your system and when it will destroy it. In the previous chapter, we proved that a single agent hits a cognitive wall. Now the question becomes, how do you connect multiple agents without creating a worse problem? This is where most teams make their first, and most expensive, architectural mistake. They pick a topology by instinct, not by principle. In distributed systems, we have always faced this same fundamental fork in the road: orchestration versus choreography. Orchestration means a central authority, a control that explicitly directs every participant. Choreography means agents react to events autonomously, with no central coordinator at all. These are not preferences. They are architectural contracts with radically different failure modes, latency profiles, and operational costs. Before you write a single line of agent code, you must make this decision consciously, because reversing it later costs you weeks, not hours. The first classification axis is control coupling. Who holds the execution state, and who decides what happens next? Get this wrong, and every scaling attempt after it will fight the architecture instead of extending it. Stay with me, because topologies we are about to examine will map directly to failure patterns you will encounter in production. Now let us place all three topologies side by side and stress test them across 6 engineering dimensions. Centralized orchestration gives you tight control coupling, one coordinator, one source of truth. Peer-to-peer choreography gives you loose coupling through event streams, but you pay for it in consistency complexity. Hierarchical nesting sits between both. Moderate coupling within each tier, with blast radius contained to sub-teams. On fault blast radius, arguably the most important dimension for production systems, centralized orchestration is the highest risk. If the orchestrator fails, the entire workflow halts. Peer-to-peer distributes failure gracefully. Hierarchical contains it within subtrees. Latency profile tells a different story. Centralized adds coordination overhead at every hop through the orchestrator. Peer-to-peer can achieve lower latency through direct agent communication, but the cost of ordering guarantees. Observability is where centralized wins decisively. One coordinator means one audit log. Peer-to-peer choreography is notoriously difficult to trace across asynchronous event chains, a problem we solve with distributed tracing standards like OpenTelemetry. Scalability and implementation complexity are the final trade-offs. Peer-to-peer scales horizontally the best, but it demands the most engineering discipline to build correctly. But here is what the comparison table cannot tell you: which pattern destroys itself under load. Find out right now. The centralized orchestrator pattern is the most intuitive topology, and that intuition is exactly what makes it dangerous to scale. Let us trace its execution cycle precisely. Phase 1. Task decomposition. The orchestrator receives a high-level goal and breaks it into discrete subtasks, each scoped for a specific subagent. This requires the orchestrator to maintain a global dependency graph, knowing which tasks can run in parallel and which are sequentially blocked. Phase 2. Subagent dispatch. The orchestrator issues task assignments with bounded context, only the information each subagent needs. Oversharing context at dispatch is one of the most common performance killers in production agent systems. Phase 3. Result aggregation. As subagents complete their work, the orchestrator collects results, validates them against expected schemas, and merges them into a coherent intermediate state. Phase 4. Replanning. If a subagent fails or returns unexpected output, the orchestrator executes corrective replanning, reassigning the task, adjusting the dependency graph, or escalating to a fallback. This 4-phase cycle maps almost perfectly to the Saga pattern in distributed transactions, a pattern with decades of production validation. The critical insight is that the orchestrator is not just a router. It is a stateful transaction manager. and stateful transaction managers under load have a very well-documented failure mode. Watch what happens next. Here is the structural trap hidden inside every centralized orchestrator. As you add more subagents, two failure modes emerge simultaneously, and they compound each other. First, the orchestrator becomes a single point of failure. In distributed systems theory, we call this violating the redundancy principle. Every enterprise architecture standard, from TOGAF to NIST SP 800 to NIST 860, explicitly warns to SPOFs in critical workflow paths. If your orchestrator process crashes, hangs, or exhausts its context window, every in-flight subagent task becomes orphaned. There is no recovery without external intervention. Second, context accumulation. The orchestrator must track the state of every subagent interaction to make intelligent replanning decisions. With 5 subagents, this is manageable. With 20 subagents, running concurrently across multiple workflow steps, the orchestrator's context window fills with aggregated histories, partial results, and dependency metadata. At this point, the LLM powering the orchestrator begins to lose coherence, a phenomenon that has no equivalent in traditional software, but is devastatingly real in production AI systems. These two failure modes, SPOF and context bloat, are not bugs you can patch. They are structural consequences of centralized state ownership. This is not a hypothetical risk. It is the most common cause of multi-agent system collapse in enterprise deployments. And the question becomes, can you engineer around it, or must you change the topology entirely? Despite its weaknesses at scale, the centralized orchestrator pattern is not obsolete, it is simply misapplied. The key is knowing precisely when it is the correct choice. Use this checklist before committing to centralized orchestration. First, are your tasks tightly interdependent? If subtask B cannot start until subtask A's output is validated and transformed, you need a coordinator that owns that dependency. And centralized orchestration is purpose-built for this. Second, does your workflow require strict sequential execution with explicit ordering guarantees? Think regulatory compliance pipelines, financial transaction processing, or multi-step document generation where order violations produce invalid outputs. Third, is your subagent count bounded and predictable, say fewer than 10 concurrent agents? Below this threshold, context accumulation is manageable and SPOF risk can be mitigated with simple orchestrator redundancy. Fourth, do you prioritize observability and auditability over raw performance? Centralized orchestration gives you a single, coherent audit trail, invaluable for compliance-regulated industries. If you check all 4 of these, centralized orchestration is not just acceptable, it is the best tool for the job. If you check 2 or fewer, you will building toward the orchestrator trap. Next, we examine the topologies designed to escape it. Peer-to-peer choreography is the topology that microservices architects will recognize immediately, because it is the same pattern that replaced monolithic service orchestration in the 2010s. Instead of a central coordinator, agents communicate by publishing and consuming events on a shared message bus. Think Apache Kafka Dues Event Bridge, or a purpose-built agent event stream. Each agent has a defined domain of responsibility. When it completes work, it publishes a typed event. Other agents that are interested in that event type subscribe and react, no central authority required. The advantages are structural. Eliminate the orchestrator, and you eliminate the SPOF. These scale independently. Failures are isolated. The system continues to function in a degraded but operational state when individual agents fail. But this is where distributed systems veterans will recognize the familiar challenge that returns without fail: distributed consistency. Without a central coordinator, who ensures that events are processed in the correct order? Who detects that a required event never arrived? Who handles the case where 2 agents per conflicting state updates simultaneously? These are exactly the problems that led to the development of consensus algorithms, Paxos, Raft, and event sourcing patterns with idempotent consumers. Peer-to-peer choreography does not eliminate coordination complexity. It distributes it, and distributed complexity is harder to observe and debug than centralized complexity. Every agent you add is another potential source of event ordering violations. The question is, can your team own that operational burden? Hierarchical orchestration is the topology that emerges when you need centralized control at scale. And it does so by borrowing a design pattern that has worked in human organizations for centuries. The team of teams model, made famous by General Stanley McChrystal's military command restructuring and formally described in enterprise architecture as federated governance, the hierarchical pattern applies recursive delegation to agent coordination. At the top is a root orchestrator, the strategic coordinator. It does not interact with individual worker agents. Instead, it dispatches to a layer of domain orchestrators, each responsible for a bounded problem subdomain. Each domain orchestrator then manages its own set of leaf agents, applying the centralized orchestration pattern within its scope. This structure gives you three critical properties that neither pure centralized nor pure peer-to-peer can deliver simultaneously. First, fault containment. A failure in the data retrieval subteam does not propagate to the analysis subteam. Blast radius is bounded by tier boundaries. Second, context isolation. Each orchestrator only accumulates context for its own subagents, solving the context window exhaustion problem by architectural partitioning. Third, independent scalability. You can scale individual subteams without restructuring the entire hierarchy. The trade-off is latency. Every delegation hop adds coordination overhead. But for complex, long-running workflows where correctness matters more than speed, this is the topology that survives production. And the decision between these three topologies is not always permanent. The final scene will give you a portable selection matrix. We have covered three topologies with enough depth to make an informed architectural decision. Let us consolidate this into a portable sortable selection matrix, the kind of reference tool you would include in a technical design document or a exam response on distributed agent architecture. Map your use case to three axes. Axis 1, task coupling. If tasks are tightly sequentially coupled, lean centralized. If tasks are loosely coupled and event-driven, lean peer-to-peer. If tasks are modularly grouped with intergroup dependencies, hierarchical is your pattern. Axis 2, scale requirement. Small and bounded teams, go centralized. Horizontally elastic workloads, peer-to-peer. Large but structured workloads, hierarchical. Axis 3, operational maturity. If your team is new to distributed systems, centralized is safest to debug. If your team has event-driven microservices experience, peer-to-peer is within reach. Hierarchical requires both distributed systems fluency and strong observability tooling. Remember this, no topology is universally superior. The orchestrator trap is not using any one pattern. It is applying the wrong pattern to the wrong problem, then scaling it before you discover the mismatch. In the next chapter, we are going to take this knowledge and do something more uncomfortable. We will map classic distributed systems failure modes, network partition, split brain, cascading timeouts, directly onto agent architecture anti-patterns you are probably already building. If you thought the orchestrator trap was the whole story, you have not seen the second layer yet. Here is the failure scenario that kills most multi-agent systems in production. One sub-agent hangs, and within seconds, the entire orchestrator pipeline stalls. No response, no error, just silence. This is not an AI problem. This is the exact same cascade failure we solved in distributed microservices 20 years ago using the bulkhead pattern. In naval architecture, a bulkhead is a watertight compartment that prevents one flooded section from sinking the entire ship. We apply the same principle here. Each subagent must be isolated in its own execution compartment, separate thread pool, separate timeout boundary, separate failure domain. When the code review times out, the security scan agent must continue unaffected. The orchestrator does not wait for the dead compartment to recover. It seals it off and continues with partial results. The blast radius of any single agent failure must be strictly bounded at design time, not discovered at 3 a.m. in production. Without explicit bulkhead boundaries, your orchestrator becomes a single-threaded bottleneck that amplifies every downstream failure. But knowing where to draw the bulkhead boundary, that is the design decision most architects get wrong, and we will see exactly why in the next scene. Once you have bulkheads in place, the next layer of defense is the circuit breaker, a pattern borrowed directly from electrical engineering and formalized in Michael Nygaard's release, which has been the distributed systems Bible for decades. Here is how it maps to agent invocation. When the orchestrator calls a subagent, it tracks the recent failure rate in a rolling window, 5 failures within 30 seconds. At that threshold, the circuit trips to open state. In open state, the orchestrator does not even attempt to call the agent. It immediately returns a fallback response. This is critical. A fallback is not a failure. A fallback is a pre-engineered degraded response that keeps the overall system functional. For example, if the dependency analysis agent is unavailable, the fallback might be a cached result from the previous run or a simplified heuristic answer. After a configured half-open timeout, one probe request is allowed through. If it succeeds, the circuit resets to closed. If it fails, open state is extended. The retry policy must also be distinguished from the circuit breaker. Retries operate within the closed state with exponential backoff and jitter to prevent thundering herd. Together, these two patterns give you a production-grade agent invocation layer. But there is a third problem that neither bulkheads nor circuit breakers fully address. What happens to time itself as it flows through the pipeline? The third failure mode is subtler than a crash. It is time starvation. Consider an orchestrator with a 30-second SLA. It calls agent A, which calls agent B, which calls agent C. Each leg of the chain independently sets its own 30-second timeout. The total pipeline can now take 90 seconds, 3 times the SLA, and every timeout fires independently, leaving the orchestrator with no coherent signal about where time was lost. The solution from distributed systems is deadline propagation, also context cancellation in Go's standard library and cancellation token in .NET. The orchestrator sets one absolute deadline, say 2.25 seconds, and passes that deadline context down to every subagent. Each subagent subtracts a processing budget, passes the remaining deadline further downstream, and cancels immediately if the remaining budget is below a minimum viable threshold. Table shows a collocation example for a 5-agent pipeline with a 30-second total budget. Notice that the leaf agents receive the smallest budgets, because context propagation overhead accumulates. This is timeout budget allocation by design, not by accident. The alternative, letting every agent independently manage its own timeout, is one of the most common anti-patterns we see in production multi-agent deployments today. In the next section, we move from time failures to structural failures, deadlock and race conditions in agent collaboration. Deadlock is not a theoretical concern in multi-agent systems. It is a production reality that most teams encounter within the first 2 months of running collaborative agent workflows. Here is the classic scenario. Agent A is performing code analysis and needs a lock on the shared code context object. Agent B is performing security scanning and holds the context lock, but it needs the dependency graph that Agent A is currently building. Neither agent can proceed. Neither agent times out because both are technically active. They are simply waiting. This is a circular dependency in the wait for graph, a formal concept from operating systems theory that maps directly to agent resource contention. The wait for graph has a cycle. A waits for B, B waits for A. Deadlock detection requires building this graph at runtime and identifying cycles. Prevention requires enforcing a strict total ordering on resource acquisition. If all agents always acquire the code context lock before the dependency graph lock, cycles are structurally impossible. In agent systems, this means your orchestrator must enforce a canonical resource acquisition. Ad hoc tool calling without lock ordering is a deadlock waiting to happen. The deeper danger is that these deadlocks are invisible. No exception is thrown, no error is logged, the system just stops making progress. Detecting and preventing them requires deliberate architectural discipline. But deadlock is only one of 3 concurrency hazards. The next one, race conditions in shared state, is even harder to reproduce. Even without deadlock, shared state in multi-agent systems introduces a consistency problem that echoes the CAP theorem debates from distributed database design. When 2 agents simultaneously read and write to a shared memory store, for example, a conversion context or a code analysis cache, you face a fundamental choice. Do you enforce strong consistency, or do you accept eventual consistency? Strong consistency means every reread sees the most recent write. This requires coordination, locks, transactions, or a single writer protocol. The cost is latency. Agents must wait for writes to be acknowledged before proceeding. In a high-throughput agent workflow, this serialization becomes a bottleneck. Eventual consistency means agents may read data, but writes propagate asynchronously, and the system converges to a consistent state over time. The cost is correctness risk. 2 agents may act on divergent views of the world and produce conflicting outputs. The right choice depends on the semantics of the shared data. For immutable context that is written once and read many times, strong consistency is cheap and correct. For continuously updated working memory where reads and writes interleave, you need a conflict resolution strategy. Last writer wins, merge functions, or vector clocks borrowed from CRDTs. The critical insight for the exam and for your architecture review. The consistency model is not a database decision, it is a business logic decision about what it means for 2 agents to disagree. And the cost of getting this wrong is not a database error. It is a silent wrong answer delivered to your user. The third concurrency hazard is the one most teams overlook entirely until it causes a production incident. Non-idempotent agent tool calls. Here is the scenario. An agent calls a database write tool. The network is slow. The orchestrator does not receive an acknowledgement within the timeout window. The circuit breaker is closed, so the orchestrator retries the call. But the first call had actually succeeded. The acknowledgement was simply delayed. Now the write executes twice. If the tool call is not idempotent, you have a double write, a duplicate record, a double charged payment, a code change applied twice. In distributed messaging theory, this is the at least once delivery problem. The solution is idempotency keys. Each tool invocation must carry a unique idempotency key generated by the orchestrator. The tool implementation checks whether a call with that key was already processed. If yes, it returns the cached result without re-executing. This is not optional in production. It is a contractual requirement between the orchestrator and every tool it calls. Let me give you the production checklist right now. These are the conditions every agent tool call must satisfy before you go live. You have deployed your multi-agent system. Something goes wrong. A user reports that the code review pipeline returned an incomplete analysis. Now you need to answer. Which agent failed, at what time, with what input, and why? Without distributed tracing, your answer is, I do not know. This is the exact crisis that drove the adoption of open telemetry and microservices architectures, and it maps perfectly to multi-agent systems. The core concept is the trace, a single end-to-end execution journey identified by a globally unique trace ID generated at the orchestrator entry point. Within that trace, each agent invocation creates a span, a timed unit of work with a start timestamp, end timestamp, and status. Spans have parent-child relationships. The orchestrator span is the root. Each subagent invocation is a child span, and each tool call within an agent is a grandchild span. The critical implementation requirement is trace ID propagation. When the orchestrator calls a subagent, the trace ID and parent span ID must be passed as part of the invocation context, not as application payload, but as explicit tracing headers or context metadata. Every agent must extract these identifiers on entry and use them when creating its own child spans. Without this propagation, you get disconnected islands of telemetry with no way to reconstruct the full execution path. Open provides the semantic conventions for this today. The question is not whether to instrument. The question is whether you instrument before the first production incident or after. Distributed traces tell you where time was spent and where errors occurred. But in a multi-agent AI system, there is a third question that traces alone cannot answer. Why did the agent make that decision? This is the LLM reasoning trace problem, and it is architecturally distinct from operational telemetry. When an agent decides to call tool A instead of tool B, or when it produces an unexpected output, you need to capture the full reasoning chain. The system prompt that was active, the conversation context that was passed, the LLM's intermediate chain of thought, if chain of thought prompting was used, the specific model version and temperature setting, and the raw token level output before any post-processing. This is not a debugging nicety, it is a compliance requirement under emerging AI governance frameworks. The EU AI Act's transparency provisions for high-risk AI systems explicitly require audit trails of automated decision-making. NIST's AI risk management framework similarly emphasizes explainability as a core governance control. Architecturally, this means every agent node must write a structured reasoning log entry at each invocation. Immutable, append-only, with tamper-evident checksums. The reasoning log is separate from the operational trace. It lives in a compliance store with longer retention and stricter access controls. Teams that skip this steps unable to explain a production decision 6 months later, and in a regulated industry, unable to explain means unable to operate. We now have all three layers of the observability model applied to multi-agent systems. This is the same three-signal model that every mature SRE practice uses for microservices, law, tricks, and traces, but each signal has agent-specific semantics that you must explicitly design for. Logs capture discrete events, agent invocations, tool calls, errors, and the reasoning audit entries we just discussed. Metrics capture continuous measurements, latency percentiles, tool call success rates, circuit breaker state counts, LLM token consumption, and cost per workflow. Traces capture the causal execution graph, how work flowed from orchestrator to subagents to tools and back. No single signal is sufficient alone. Metrics tell you something is wrong. Traces tell you where it went wrong. Logs tell you why. Together, they form the observability stack that makes a multi-agent system debuggable, governable, and improvable over time. The architecture principle here is, observability is not a feature after deployment. It is a structural property you design in from the first agent boundary. In the next chapter, we move from theory to production reality. We will build a complete code review agent system using the model context protocol, applying every pattern from this chapter to a working reference architecture. In the previous chapter, we mapped classic distributed systems failures, split brain, cascading timeouts, thundering herd, directly onto agent architecture patterns. Now it is time to stop diagnosing problems and start building solutions. Let me show you a production-grade multi-agent system I helped architect for a mid-sized fintech engineering team. The system has one job: automate the entire code review lifecycle. At the center sits an orchestrator agent. It receives a pull request event and immediately delegates to three specialized running in parallel: the code review agent, which analyzes logic correctness, security vulnerabilities, and style compliance. The documentation agent, which evaluates inline comments and generates missing docstrings, and the test generation agent, which identifies unstd branches and proposes new test cases. Each agent is a fully isolated reasoning unit with its own context window, its own tool bindings, and critically, its own failure boundary. This is not 3 LLM calls chained in sequence. That would be the anti-pattern we demolished in Chapter 4. This is a genuine fork-join topology borrowed directly from parallel computing. But here is the question you should already be asking. What happens when these 3 agents return contradictory findings about the same code block? That answer is coming in the very next scene. Let us walk through the fork-join execution pattern step by step, because the devil is entirely in the merge phase. Step 1. The orchestrator receives the pull request payload and normalizes it into a shared context object, the diff, the file tree, and the commit metadata. Step 2. It dispatches all 3 subagents simultaneously. This is not sequential chaining. All 3 run in parallel, typically completing within the same latency window as a single agent call. Step 3. And this is where most teams get it wrong, is the result merge. What happens when the code review agent flags a function as having insufficient error handling, but the test generation agent proposes a test that implicitly assumes that same function succeeds? These outputs conflict. You need a defined resolution policy before you write a single line of code. In our production system, we implemented a 3-tier conflict resolution strategy. Structural conflicts, where one agent's output directly contradicts another, are escalated back to the orchestrator for a secondary reasoning pass. Semantic overlaps are merged with a priority weighting where securities always supersede style findings, and additive outputs, documentation plus tests, are simply concatenated. The key insight here, borrowed directly from distributed consensus theory, is that you must define your conflict resolution policy at design time, not at runtime. And yet, even with a perfect merge policy, there is still a deeper structural question. Are these agents actually doing different jobs, or are they just doing the same job with different prompts? That distinction is everything, and we are about to draw that line precisely. The single responsibility principle is not a back-end software engineering nicety. It is a load-bearing architectural constraint for multi-agent systems. Let me show you exactly why with a comparison table. When we defined the code review agent, we gave it exactly one domain: correctness and security of the existing code. It has no awareness of what tests exist or what the documentation says. That constraint is intentional. A fat agent that tries to simultaneously reason about logic, tests, and documentation will hallucinate cross-domain interference. It starts making security recommendations that assume test coverage that does not exist. The documentation agent is scoped to the human readability contract. Does the code communicate its intent clearly to the next developer? It has no business forming opinions about logic correctness. The test generation agent operates purely in the behavioral specification domain. Given this code, what observable behaviors should be guaranteed? Notice that none of these agents share a context boundary. Context pollution, where an agent's reasoning about one domain bleeds into and corrupts its reasoning about another, is the silent accuracy killer in production systems. This is directly analogous to the bounded context pattern in domain-driven design. Each agent is a bounded context with a strict anti-corruption layer at its interface. The payoff of this discipline is measurable. In our fintech deployment, single-agent code review produced a 34% false positive rate on security findings, after decomposing it into specialized agents that dropped to 11%. Specialization is not an abstraction preference. It is a precision instrument. Now that we have the agents defined and their boundaries drawn, we need a standardized way to actually use tools. That is where MCP comes in, and it changes everything about how you wire agents to the real world. Every distributed system eventually faces the same integration tax. In the microservices era, every team was writing bespoke HTTP clients, custom serialization logic, and one-off retry policies for every service-to-service call, until REST gave us a uniform interface contract, and later gRPC gave us typed, versioned contracts with bidirectional streaming. Multi-agent AI systems are hitting the exact same wall right now. Every agent team is handcrafting custom tool integrations. A bespoke GitHub API wrapper for this agent, a custom Jira client for that agent, a one-off database connector for the next one. The operational overhead compounds with every new tool, every new agent, and every model upgrade. The Model Context Protocol, MCP, is the answer to this integration tax. MCP is an open standard introduced by Anthropic in late 2024 that defines a uniform contract layer between any AI agent and any external tool or data source. Think of it as the rest of agent tool integration. It does not care which LLM powers your agent. It does not care which tool you are connecting to. It defines a protocol-level contract, how tools are described, how agents discover them, and how invocations are structured and returned. In our code review system, this means all three subagents, regardless of their domain specialization, use the identical MCP interface to access the GitHub API, the static analysis engine, and the test runner. When we upgrade the underlying model from Claude 3.5 to Claude 4, zero tool integration code changes. That is the contractual promise of a standardized interface layer. But the protocol itself has a specific architecture that you need to understand before you integrate it, and it is more elegant than most people realize. The MCP architecture is elegantly simple once you understand its two-sided structure. On one side, you have MCP servers. These are the tool providers. Each MC server wraps one or more external capabilities: a GitHub server, a static analysis server, a database query server. The server exposes a tool manifest, a machine-readable declaration of every tool it offers, including the tool name, a natural language description the LM uses to decide when to invoke it, the input schema, and the output schema. On the other side, you have MCP clients. These are embedded within your agents. The client has two responsibilities. First, capability discovery, where it queries the server's manifest at startup and builds a local registry of available tools. And second, invocation, where it serializes the agent's tool call into a standardized MCP request, sends it to the server, and deserializes the response back into the agent's context. Notice what this eliminates. The agent never needs to know the implementation details of the tool. It never manages authentication tokens directly. It never handles retry logic at the tool layer. That is the MCP server's responsibility. This is the separation of concerns principle applied to agent-tool integration. In our code review system, the MC GitHub server handles OAuth token refresh, remit backoff, and response pagination. All three subagents call it through the identical client interface and receive clean, normalized responses. And here is the architectural implication that most teams miss. Where exactly does MCP sit in your full multi-agent stack? That positioning question determines whether your architecture scales or collapses under production load. Let me now position MCP precisely within the full multi-agent architecture stack, because this is where I see the most architectural confusion in production teams. The Orchestrator sits at the top of the decision hierarchy. It does planning, delegation, and result synthesis. Subagents sit at the execution layer. They do domain-specific reasoning. MCP occupies the tool-binding layer immediately below the subagents. And critically, the Orchestrator itself also has an MCP client. Why? Because the Orchestrator needs its own tools too. It needs to read the PR metadata, write the consolidated review comment back to GitHub, and trigger CI pipeline events. This means MCP is not just a sub-agent concern, it is a system-wide interface standard. The protocol boundary that MCP enforces is the clean separation between reasoning and execution. Above the MC boundary, LLM reasoning. Below the MCP boundary, deterministic tool execution. This boundary is your observability insertion point. Every MCP invocation is a structured, loggable event. In our fintech deployment, we pipe all MCP call logs into our existing distributed tracing infrastructure, the same Jaeger traces we use for microservice calls. Multi-agent debugging becomes identical to microservice debugging. That unification is the architectural payoff you have been building toward across this entire lecture. Now, with the architecture fully defined, the final question remains: how do you decide which pattern to use for your specific system? The architecture decision record, coming next, gives you a reusable framework for exactly that decision. Every architecture decision made under deadline pressure without a documented rationale becomes a liability. The architecture decision record, the ADR, is the tool that distributed systems architects have used for decades to capture not just what was decided, but why, and what trade-offs were consciously accepted. I am now giving you an ADR template specifically calibrated for multi-agent topology selection. The four variables you must assess before choosing a topology are task coupling, fault tolerance requirement, latency budget, and team operational capacity. Task coupling asks, are the subtasks truly independent, or does task B require the output of task A to begin? High coupling mandates sequential pipeline topology. The code in task literally cannot run without task A's output. Low coupling enables parallel fork join, which is what we built in our code review system. Fault tolerance requirement asks, if one subagent fails, can the system deliver partial value, or does the entire workflow fail? If partial value is acceptable, as it is in code review, where a review without documentation suggestions is still useful, you implement independent failure domains with graceful degradation. If all or nothing semantics are required, financial reconciliation, for example, You need distributed saga patterns with compensating transactions. Latency budget determines whether you can afford the orchestration overhead of multi-agent coordination. For sub 250 ms P999 requirements, a single optimized agent almost always wins. For tasks where 530 seconds is acceptable, parallelism provides dramatic throughput gains. And team operational capacity is the often ignored variable. A 3-person team cannot operationally sustain a 7-agent system. Every agent you add is a production incident waiting to happen if you do not have the observability and runbook infrastructure to support it. The next scene will show you exactly when this discipline breaks down, and the cost of ignoring it. I want to close this chapter with the most important warning in this entire lecture series. The most dangerous failure mode in multi-agent architecture is not under-engineering. It is over-engineering. Premature agent decomposition. Splitting a task into multiple agents before you have evidence that a single agent cannot handle it is the fastest way to multiply your operational costs while simultaneously degrading your system's reliability. Consider the comparison. A single agent solution for a simple code quality check has a total operational surface of 1 model call, 1 set of prompts to maintain, 1 failure mode to monitor, and 1 deployment artifact. A 3-agent system for the same task triples every one of those numbers and adds inter-agent communication overhead, conflict resolution logic, and distributed tracing infrastructure on top. If the task does not genuinely require parallel specialization, if it does not have low coupling, sufficient latency budget, and team capacity to support it, then the multi-agent architecture is a net negative. The Yagini principle, you ain't gonna need it, applies to agent decomposition as brutally as it does to microservice decomposition. The engineering community spent 5 years over microservicing monoliths, and then spend the next 5 years building them back into modular monoliths. We are at the exact same inflection point with multi-agent systems today. Start with a single, well-prompted agent. Measure where it fails. Decompose only the dimensions where specialization demonstrably improves outcomes. This is the architectural maturity that separates engineers who build systems that survive production from engineers who build architectures that impress whiteboards. In the final chapter, we will synthesize everything: the distributed systems principles, the failure patterns, the MCP protocol, and the ADR framework, into a unified intuition you can carry into any agent architecture problem you face. We have covered 6 chapters of dense architectural thinking. And now it is time to stop adding new concepts, start connecting everything we have built. A senior architect's greatest skill is not memorizing patterns in isolation, but seeing how they compose into a single coherent system of thought. Look at this concept map. On the left side, you see the topology layer, orchestrator subagent, choreography, hybrid mesh. Each topology carries a specific coordination cost and a specific failure blast radius. On the right side, you see the distributed systems principles that govern every topology: fault isolation, eventual consistency, idempotency, circuit breaking. These are not AI-specific ideas. They are 25 years of hard-won distributed systems wisdom, now reapplied to agent networks. The center of the map is the intersection, MCP as the protocol layer that makes tool invocation observable and auditable, regardless of topology. Every keyword in this lecture lives somewhere on this map, and every arrow between them represents a design trade-off you must consciously make. If you cannot draw this map from memory before your next architecture review, you are not ready to deploy a multi-agent system at scale. But knowing the map is only half the battle. The other half is knowing which 5 rules to never break. Every architecture decision eventually comes down to a checklist. Not because checklists replace thinking, but because under deadline pressure, experienced architects still forget the basics. These 5 rules are distilled from everything in this lecture, and each one maps directly to a failure mode we analyzed. Always assign topology before assigning models. The topology determines your coordination and cost ceiling. Choosing models first is like picking furniture before drawing the floor plan. Rule 2. Treat every subagent boundary as a distributed service boundary. This means explicit contracts, versioned interfaces, and no shared mutable state. Rule 3. Design for partial failure as the default, not the exception. Every agent call must have a circuit breaker, a timeout, and a compensating transaction plan. Rule 4. Instrument before you deploy. If you cannot trace a single task request through every agent, hop with a correlation ID, you are operating blind in production. Rule 5. Validate your context budget under realistic load. A system that works with 3 concurrent users will silently collapse under 30 because nobody measured token accumulation under parallel execution. These 5 rules are your pre-flight checklist. Ignore any one of them, and your multi-agent system will eventually fail in production. The only question is when. And now that you have the complete architecturation, the question is, what comes next? You have now mastered topology and fault isolation. But there is a dimension of multi-agent architecture we have deliberately deferred until this moment: memory. Every agent in our systems so far has been functionally stateless between invocations. The orchestrator passes context, subagents execute, and the result is returned. Enterprise workflows are not single-shot transactions. They are long-running processes where an agent must remember what it did 3 days ago, learn from past failures, and carry procedural knowledge across thousands of sessions. This is the agent memory architecture problem, and it is the immediate next complexity frontier. Think of it in 3 layers, borrowed directly from cognitive science and mapped to distributed storage patterns. Episodic memory, what happened in past sessions, maps to a vector database with RAG retrieval. Semantic memory, factual domain knowledge, maps to a knowledge graph or structured retrieval index. Procedural memory, how to perform a task, maps to fine-tune model weights or catch tool execution plans. The critical architectural question is, which memory layer should an orchestrator manage and which should live inside the subagent? Get this boundary wrong, and you recreate the shared mutable state problem at the memory layer. A distributed systems anti-pattern that will corrupt your agent's behavior in ways that are almost impossible to debug. The answer to that boundary question is what our next lecture will address in full. And it will challenge assumptions you do not even know you are making right now. We end where every mature engineering discipline must eventually arrive: the question of how you know your system actually works. For traditional microservices, we have decades of battle-tested evaluation frameworks, load testing, chaos engineering, contract testing, SLA benchmarking. For multi-agent AI systems, we have almost none of that infrastructure. This is the single most underestimated production risk in enterprise AI today. How do you load test an orchestrator when the subagent responses are non-deterministic? How do you write a contract test when the agent's output schema can drift with every model update? How do you run chaos engineering on a system where injecting a single failure triggers cascading LLM retries that cost real money per token? These are not theoretical questions. They are the questions your ops team will ask you the week after you deploy. The emerging answer is simulation environments, synthetic task generators that produce realistic multi-agent workloads, golden trace datasets that define expected agent behavior without requiring deterministic output, and statistical assertion frameworks that evaluate agent correctness over distributions rather than single outputs. This is active research territory, and it is where the next generation of multi-agent infrastructure tooling is being built right now. The architect who solves the evaluation problem will define how the entire industry deploys agentic AI at scale. That problem is yours to solve, and this lecture has given you the foundation to ask the right questions. Everything you have learned here is a stepping stone. The real work begins the moment you close this session and open your architecture document.